Well, good morning. It's 11:37. We're 7 minutes late getting started for linear algebra class, but I came in the classroom, nobody was here, so I thought, well, let me run down to the restroom and maybe someone will show up before I get back. They haven't. So let's go back to where we left off. I do have some announcements I was going to make today, but I don't want to make them to an empty room, so I'll wait till at least one person comes in, then I'll make the announcements, and maybe you will be able to hear them on the YouTube videos. We're recording. Okay, I can't think of anything else, so let's move on. We're in Chapter 1, Systems of Linear Equations, Section 1.3, Applications of Systems of Linear Equations. And we're on page 30, and we're about to hit Kirchhoff's laws. And it's a little bit similar to the branching and mapping that we were doing in the last example, but a little bit different too because other things are involved. So here's basically the two principles of Kirchhoff's law. Now, Kirchhoff's law deals with electricity. Now, with electricity, you have at least two things going on. You have current, three things. You have current, you have voltage, and you have resistance. And then those are connected in various ways. The first of these, the current part, is very similar to what we were doing before. All current flowing into a junction must flow out of it. It's just like the traffic patterns or the other things that we're doing in the last example last time. All the current flowing into a junction must flow out of it. That's Kirchhoff's first law. Let me get my pen set up. Rather strange name, Kirchhoff. One of the few words I know with double H's in them. And double F's, but lots of words have double F's. Kirchhoff's laws. First of these is what I call I've heard it called the junction law, and it has to do with current. Okay, all current flowing into a junction must flow out of it. Okay. Now, the second of these is often called the loop law. Okay? And what this means, if you go around any circuit loop, okay, any complete loop, the sum of the products of the resistance, you call it the voltage drop, I times R, around the closed path is equal to the total voltage in the path. Okay, that's one way to express it. The sum of the voltage drops and that's your I times R, that's the voltage drop, where I is the current and R is resistance. The sum of the voltage drops in any current loop is equal to and they call it, they said a closed path, I call it a current loop, is equal to the applied voltage in the path. Okay, I'm calling it loop, they're calling it path meaning closed path. Now, just a little bit of background. In any electrical network, the current, why they give it the symbol I don't know, is measured in amps. Capital A, actually the word is ampere. We abbreviate it as amps. The symbol for it is A. Okay, that's the unit symbol. The symbol for the parameter current is I. Okay, don't get those crossed up. A always has a number in front of it, 7 amps, 4 milliamps, whatever. Okay. Resistance is in ohms. The R is the resistance. And that's the symbol capital Omega. Okay, Ohm. Named after Georg Ohm, who did the early work with resistance and came up with Ohm's law and various things like that. And then you have the voltage, and this is one of the V stands for the voltage. This is usually applied voltage, not the voltage drop. Okay, the unit for voltage is also volt, named after Alessandro Volta, and so that's why it's capitalized, just like A is named after Louis Ampere, so that's capitalized. And even the resistance, omega, that's a capital Omega because it's named after Ohm, okay, Georg Ohm. But you might say, why don't you use an O? Why do they use omega? Well, give me a number of ohms, like 5 ohms. What if it was O? That looks like 50 to me. So it would be hard to distinguish O from 0. So that would make it, that's one reason they didn't use O, capital O. Well, they could have gone, and they did go to the Greek alphabet, but the letter corresponding to O in the Greek alphabet is Omicron, and it looks just like an O, so that doesn't work either. But the Greek alphabet has 2 letters that begin with O. Omicron is in the position of our letter O, or very close to it, shortly after mu and nu, then Omicron. But the Greek alphabet has another letter that starts with O, and that's the very last letter in the alphabet. They don't have a zeta or anything else that corresponds to our Z. They have an omega, and that's where they get this one. And that's the omega, because I have to distinguish it from Omicron, so it's that symbol omega, and that's the one they use, capital Omega, for resistance, named after Ohm. So, that said, a little bit about how you draw these things, okay? Current will usually indicate, if you got a wire going here, we'll just indicate with an arrow and call it I1 or something like that, okay? If you have a resistance, that's usually designated as a jagged line like that, and that might be R1 would be 5 ohms or something like that. And your voltage is usually represented, so good to see you. I hate talking to myself. I feel like I'm going nuts, okay? No, I'm just kidding. All right. So Keystons here. And get the date in. All right. Let me get a few things swapped around here. Injured my knee a little over the weekend, so I'm moving kind of slowly. And I had said also on the video that I would make the announcements after I had at least one warm body here, so I hope you are warm enough. Okay. So, here are the announcements. I have several this time. I finally had a chance yesterday to print off a few, and there's a lot of things at the first of the term that get started. And here's one. Have you heard of the Scholars Bowl? Okay. Mr. West is our coach for that, and here's what he asked us to announce. The Lawson State Scholars Bowl is recruiting players for the 2019 to 2020 season. Scholars Bowl is a competition of questions and answers played by teams with buzzers. Questions are read and the players buzz in without consulting with each other when they think they know the answer. If they give a correct answer, they earn points plus a bonus question in which they can work with their team to earn additional points. Questions cover a wide range of academic topics, mostly from science, literature, history, fine arts, geography, philosophy, the social sciences, plus pop culture, sports, and current events. Lawson State team practices every week and competes against other colleges about 2 or 3 times each semester. The first practice and the first interest meeting is day after tomorrow, Thursday, September the 12th, 12 o'clock down in room 261, down this little half flight of stairs, second classroom on the left. It's about 2/3 of the way down the hall, second classroom. Okay. And it's not exactly like Jeopardy, but that's what they use as a board because you have a variety of topics and things. The Scholars Bowl is currently recruiting players with knowledge in any subject, including history, literature, science, music, current events, mythology, and mathematics. Okay, so there we have that. We also have a math team, and the first math team meeting will be this Friday. It's coming up Friday. And it'll be from 10 till 12, though it may not go that long, over in the Birmingham West Campus in the Science Building, and it's room C103, which is usually they used to meet in 100, but there must be a class in there, so it's C103. The C building is a very short building, so it's pretty easy to find. This is something, another possibility. This is from the Miss Stacy Schmidt, or Mr. Stacy Schmidt. It could be either one. It doesn't indicate. The Gulf Coast Regional Coordinator recruiting on behalf of the NASA Community College Aerospace Scholars Program. It's abbreviated NCAS, okay? And we've had several students from Lawson participate in this, and everyone that I've heard about really thoroughly enjoyed it. They actually occasionally will get to interact with a space program going on, a shuttle program. They don't have shuttle anymore, but something that's going on at the space station and collecting data or a variety of things. They've really found it very interesting. So if you're interested in this, there's lots of websites you can go to. I won't read them all off. There's all of them start with go.nasa.gov, but then different slashes take you to different areas. They have. What's that? I'm sorry?
Is that like an internship?
Yes, what? Yeah, it's like an internship. It's that type of thing. That NCAS, that was from last year, but that was their thing there.
Is it paid?
What's that?
Is it paid?
Yeah. There's the variety of levels that they do things for it. Let me see if I can get this. Top performing students can earn an invitation to a 4-day residential engineering design challenge during either the spring or summer of 2020 at a NASA center. NASA pays for travel, lodging, and meals. The invited students only pay for a $35 registration fee. But to participate in the program itself, let's see. if your students apply and meet the eligibility requirements, then you can click and see what those are. We invite them to a 5-week online learning experience. While in the course, students learn about the history and future of NASA exploration, talk with NASA scientists, engineers, and complete a final project. So I don't know. I think based on what I remember from some of the other students who participated, it was nominal pay for an internship, but it's mostly done here, and you do it online type stuff. But then when they do send you somewhere, they'll pay for parts of that. I wish I knew more, but you can go and find out. They have a e-flyer, a website, and a video that they probably explain that a lot more. So you're welcome to take this and read it. Now this one more, this was in my box this morning. I found it pretty interesting. The Board of Governors of the Federal Reserve System. So why have I got a letter from them in my box? But they have a couple of opportunities. The first is called the College Fed Challenge. It's a competition in which teams act as members of the Federal Open Market Committee and present their monetary policy recommendations to a panel of judges. And then if you do well, you can move way up. And actually, the finals are hosted by the Board of Governors of the Federal Reserve. Team members get to meet the Fed Chair, Mr. Jerome Powell. So that's pretty impressive. Then there's another thing, and there's more information here. There's another one that's exploring careers in economics. The event offers students a chance to speak with research assistant staff and economists about the field generally, as well as career opportunities within the Federal Reserve System. And again, I don't have any more details of that. It says they do a lot of stuff in person, webcast. You can go and watch the live broadcast about it, October 11th. And there's plenty of sites you can go to find out more. So, sorry, there's not too many specifics here, but you're welcome to take these and look at them if you're interested in any of those. Okay, we were just talking about, or I was just talking about Kirchhoff's laws. This is where we dropped off last time, and it's a little bit similar to the kind of networking things that we did last time, where you had nodes where things were coming in and leaving. The first part of this is like this. All current flowing into a junction or a node must flow out. So that's very similar to what we did before. The difference here is that you also have, in addition just to current, you have voltages and resistors in these circuits. And the sum of the voltage drop, which is how much voltage is used by a resistor, which is the product of the current times the resistance, that's the voltage drop, in any current loop, any closed loop within the current, is equal to any applied voltage that is in that loop. So if you have a battery source or something like that in there, then the total voltage drops must equal the total voltage that is boosted. And then I just was giving a few of the symbols. The symbol, the parameter for current is I. Where they get that, I don't know. The unit for current is amps. You would always precede that by a number. 5 amps, 4 milliamps, whatever. Okay? Resistance, the parameter is R. Its unit is ohms, named after Georg Ohm, who did early work with it, and this is Ohm's law right there, voltage is equal to IR. But because an O wouldn't be a good thing to name the unit, because 5 ohms would look like 50. That would be confusing. So they went to the Greek alphabet. In the Greek alphabet, the letter that corresponds to our O is omicron, and that's the same symbol. So that wouldn't do any good. But the Greek alphabet has a second letter that starts with O, and that's at the very end of their alphabet, and that's the omega. And that's why they use that symbol, and that's the capital omega because it is named after somebody. Amps are named after Louis Ampere, a French physicist who did early work with current, and Georg Orum, a German mathematician or physicist, did the early work study of resistances, and so they named the unit of resistance after him. Now, voltage is rather unusual. And this is the symbol for current. Usually, the wire is just a line, and if you've got a current, you'll put an arrow showing at least your anticipated direction of that current, and you list the current over that and say how many amps it is. Resistance in a circuit diagram, you put the jagged line there, that indicates you have a resistor. It could be a light bulb, a heater, air conditioner. I mean, it could be anything that uses the current. The voltage, the symbol is capital V for voltage. The unit is volts, which is also capital V. And that's named after Alessandro Volta, who did some of the earliest studies on batteries and voltages. And I was lucky. My wife had a professional meeting one year in Lake Como, Italy, which is way north in Italy, right next to Switzerland, and beautiful area. And it happened to be the weekend between terms, so I got to go with her. And while she was at her meeting, she also took one of her nieces with her. And while she was in the meeting, the niece and I sightseeing, went around sightseeing. And it was this beautiful gazebo-type area, just a real pretty thing right by the lake. So we decided to walk on over and see what that was. And I found out that's where that Volta came from Lake Como. And so they had sort of a mini museum there that people could visit and see some of his early experiments and things like this. So we got to see Volta's, some of his, he called them stacks rather than batteries, but that's what we had. And so they named the unit after him, and basically the symbol for voltage is also capital V. So now I was just about to draw how they represent a voltage, especially with direct current, though it doesn't have to be. Usually one end is a long bar and the other is a short bar. That indicates a cell in a battery, okay? And just generally, each cell is usually 1.5 to 2 volts. So if you had 3 of those together, that might be anywhere from 7.5 to 9 volts or something like that. So, and you could put the short bar first and long one. Usually this is the positive side of the battery. This is the negative side of the battery. And then the other issue here, most of the time we use the conventional means of representing the current, which would be going from the long side to the short side. You know, it would be going in that direction. But in reality, electrons flow in the opposite direction because they're negatively charged. But we count on positive current. So it's a little confusing, but don't let it bother you. Okay. Now, that finishes the background. Let's actually do a problem with it. This will be example 6 on page 30, about the middle of the page. Okay. All right, to erase. Okay. Now, here is your circuit diagram. All right, we have a node here. They call it node 1. You can call it junction 1. That's what they usually call it, is junctions. Okay? Now, they list what they think the current will be, but they may be wrong. Okay? If they are wrong, our currents will come up negative, and that means they're going in the other direction. So here is what they list. They list the current as flowing to node 1 from above, and it's coming through a resistor R1, and that resistor is 3 ohms. Okay? Now, they'll claim this current is let's call that I1. Now, one of the reasons they say that it's going in that direction is because they put the long side of the battery there and the short side behind it, and they list this as, they don't give it a name. They could have called it V1, but they didn't. They just say this is 7 volts. And that would push the current in that direction. So I think their I1 is probably correct. Okay? Now, leaving node 1, you hit another resistor. And this is R2, and R2 is 2 ohms. Okay? And they come over here and meet at node 2. So this has the current leaving node 2 here and coming into node 2 there. Node 2 there. Now this one's not real clear whether it's flowing the right direction or not, but they're going to call this I2 and have it going to the right. They may be right, they may be wrong, we'll see. Okay? If you wind up, when you do your calculation, I2 comes up negative, that means they pointed in the wrong direction. Now, they also have an I3 coming in, and they say it's coming in this way, and that's coming from another resistor, R3, and R3 is equal to 4 ohms. Okay. It hits the battery, and again the long side of the battery is here, the short side there, and they claim this is an 8-volt battery. Okay? Now that would tend to push the current in this direction, so I think I3 is also probably correct in its direction. Okay? Because that would be, so if it's pushing that way, then it would be coming this way. Now, with those in mind, almost certainly I2 is running in the right direction. There's no way that I3 could be coming this way, I1 coming this way, which is what the batteries are pushing this way, and not have, you can't have I2 coming this way too, then that would be a big sink. So I2 must be heading out that way. So I think they've drawn the diagrams correctly. You got 2 nodes here, and you have at least 3 loops. They are only going to show 2 of them. Here is one loop, like that, and here's the other loop, like this. Okay? So those are your loops for Kirchhoff's loop laws. The 2 nodes are the node laws, or the junction laws. Junction law. So let's take node 1, and we're going to use Kirchhoff's junction law first. Okay, coming into node 1 is I1. So I1 plus I3 has to equal, going out the other way, I2. Okay. And that sort of makes sense. If you got both of them coming in, you're going to have a pretty good sized current flowing out. Okay? Now, if you went to node 2 and said I2 is flowing in and I1 plus I3 are flowing out, that's really the same equation you have here. It's just flip sides. So that doesn't add anything new. We're not going to do one for that loop. Okay? Now, you could, if you wanted to, do another loop. And that loop could be the outside loop. Now here you have to decide which way you think things are getting pushed. Is the 8 volt pushing harder against the 4 ohm resistor and backing up against this one, if you went this way, this would be a positive 8. That would be a minus I3 times 4 times I3. And this would be, because you think the current's going this way, and you're going against the current, that would then be a plus I1, 3 times I1, and then this would be a minus 7 because you're going against the voltage. That could be an outside loop as well. Those are usually a little weirder. Sometimes it makes good sense. But these two gives you everything you need. Those are the easy two. So let's do those two. And there's a couple ways you can do it. I like to start just past the battery here, okay, and start going this way. So here we have, like I said, the voltage drop here is going to be I1 R1. Well, R1 is 3, so this is going to be 3 I1. And then this is in the same direction of the current. That would be 2 I2. Okay, is equal to 7 volts. What do you say? Yeah, I'm starting here just past the battery, okay? And this is dropping voltage here. Okay, you could call it negative if you want to. I'm just calling it a voltage drop of 3 times I1. You could make it negative if you're, okay. Have you had this before?
Wow.
Yeah. Different people do it different ways. If you were going this, yeah, you could say minus 3 I1 minus 2 I2 plus 7 equals 0. And there, the voltage around the loop is 0. That's how they usually say it.
So, like, why did you choose to leave negative?
Because it's a voltage drop. You're losing voltage when you go across a resistance. That's why I call it just a voltage drop. 3 I1 plus 2 I2, that's your voltage drop on this side. Your voltage increase on that side is plus 7. So the voltage drop equals the voltage boost. They have to be equal for them to be 0.
Okay, the way it was talking to me.
Yeah.
I like that for like, because it's less confusing. But like the way they basically talking was that like like the direction
Right.
you choose to go in the loop is
Yeah.
arbitrary, like you pick any direction. But like if you come across a current going the same way as the direction you chose,
Yeah.
if it's going the same way across the resistor,
Right.
then it ends up being negative.
Negative, exactly.
It's going against the you need the positive.
Yeah.
So like,
Yeah. If I were doing it that way, I'd start right here then. I'd say you go up a voltage, because you see you're going up from negative to positive, right? So plus 7 volt, then you drop 3 times I1 volts, then you drop another 2 times I2 volts, and you come back here, that's equal 0. And that's exactly,
oh wait. I see this.
yeah. So what I'm doing, rather than doing these two negative, that positive, since these have a variable anyway, and this is constant, let's put this over here, and just have it equal that. Yeah, okay. Same thing down here, you get to choose the direction, and I'm going to start here, but I'm going to start just past the battery, okay? And we have a drop here of 4 I3. It's hard to read my writing there. 4 I3 plus 2 I2 is equal to 8 volts. Okay, I'm going to leave off the units now for now because it's a little too confusing. Now what we have is you almost have your matrix set up nicely. Since we're doing matrices now, before did you do it in a matrix or did you do it some other way?
We just did the old school way.
Yeah. elimination by addition or substitution or something like that. This time we're going to do this. So what we want to do is get the I2 in here. So let's subtract I2 from both sides. Okay. And here will be our system of equations. I1 minus I2 plus I3 is equal to 0. And then 3I1 plus 2I2 is equal to 7, and 2I2 plus 4I3 is equal to 8. There's our system of equations set up with variable over variable, variable over variable, variable over variable, equal sign over equal sign, and constants over constants. That's set up how we want it. And that's why I did it that way in the first place. Though, you really should have done it with the voltage up minus voltage down equals 0. But, why? I mean, this way is going to be easier than doing our thing. Well, with that in mind, let's set up a matrix. What will that matrix be? Okay. 1, negative 1, 1, 0. Okay. Second one will be a 3, 2, 0, 7. And the third one will be 0, 2, 4, 8. Okay. Now, before I do anything else, okay, I like to do things that will make things simpler in the future. And I see this bottom row, every number's even. So let's divide by 2. Okay, is that all right? So that'll make this a 1, 2, 4. 0, 1, 2, 4. Okay. Now, I may regret that later, but right now that seems like a simple thing to do. Okay. Now that I've done that, don't see anything else simple I can do. What I'm going to do now is start my row reduction. And it's sort of up to you whether you want to do Gauss or Gauss-Jordan, whether you want to do Gauss with back substitution or Gauss-Jordan, which just is going to read you out your answers. I tend to like Gauss-Jordan, so I think unless you want to do it, otherwise we will. Well, what's the first thing you want? You want there to be a 1 there. We got it without doing a single thing, so that's fantastic. We got our 1 there, so what do we want next? 0's below it. We got a 0 down here, we just need to change that. So what will we need to do to get that 3 to become a 0? Negative 3 times row 1 plus row 2 is the new row 2. Okay. Since we're using row 1, we're going to leave it alone. 1 minus 1, 1, and 0. What's our new row 2 then? Zero, 5, negative 3. Ooh, goodness gracious, that hurt. What's the last entry? 7. Got it. I just hit a funny bone, and it wasn't really funny at all. Okay. And then the last row's already got a 0 there, so I'll just write that down. 0, 1, 2, and 4. I did my new thing with it too. I'll write that down too. Row 3 divided by 2 is a new row 3. That's a legal move in most states. Okay. Now, what I think I'm going to do is erase that last equation because it's getting in the way of my matrices. We've already got it down, so I don't think it's going to lose anything by erasing it. Okay. Now, what's the next thing you would suggest doing? What's the next thing we want to happen?
I would probably swap the last.
Absolutely. We want that to be a 1. To make that a 1, you have to divide by 5. That gets messy. Okay? But it's far easier to swap these two rows because that's already a 1. And why lose that? Why not use it while we got it? So we're just going to exchange those two rows. So row 2 exchanges with row 3. And that's legal. Okay? So now we've got 1 minus 1, 1, 0. 0, 1, 2, 4. And 0, 5, negative 3, 7. Okay. Sorry. About this time, it happens on Monday, Wednesday too, my eyes start going dry. And I don't know if it's because I'm sitting over where this cooling fan for my computer blows that hot air into my eyes or what, but just all of a sudden my eyes get real stingy and I can hardly see. Now I think what I'm going to have to do is erase the, let's see, I think what I'll do is just take it up here. This will be the matrix. We'll go from there to there. Okay. So what do we want to happen next? Got a 1 here, 0 is below it. You've got a 1 here now, thanks for your swapping those two rows. And what do we want now? Bottom and top. So let's do with the top first. How are we going to get that negative 1 to become a 0? Yeah, add row 2 plus row 1 is the new row 1. Okay? So let's do that. The middle row we're using 0, 1, 2, and 4. And the new top row becomes 1, 0, 3. Is that what you said? 4. Okay? Now, what do we want to happen in the bottom row? Five to become a 0. How will we make that happen? Negative 5 plus times row 2 plus row 3 is going to be the new row 3. All right, so negative 5 row 2 plus row 3 is the new row 3. All right, so let's do it there, and what do we get? What'd you say? 0, because minus 5 times 0 plus 0 is still 0. Okay. And that becomes a 0. Now here's where it gets interesting. Negative 5 times 2 is negative 10. Minus 3 is minus 13. Ooh. Okay. And the fourth entry there, minus 5 times 4 is negative 20. Plus 7. What's negative 20 plus 7? Negative 13 again. All right. Now, what do we want to happen next? Yes, we want this to be a 1. The first non-zero entry in the third row we want to be a 1. How you make that happen is divide by negative 13. And the wonderful news is it makes both of those 1s. So if you don't mind, I'm just going to, this is, you might say cheating, but it's okay. Divide by negative 13, that becomes a 1. Divide by negative 13, that becomes a 1. Okay? That was really nasty of me, wasn't it? Okay? You probably can't do this. So it's basically row 3 divided by negative 13 is a new row 3. And we've already done that. All right. Now what do we want to happen? Zero's above it. So let's do that. We already know what I3 is. I3 is going to be 1 amp. Okay, we know that. We can look at it and see that. But let's continue our Gauss-Jordan elimination and use that bottom row, 0, 0, 1, 1. And we want that top 3 to become a 0. How do we make that happen? Negative 3 times row 3 plus row 1 is the new row 1. Okay, do it to it and see what happens. One, okay, because negative 0 plus 1 is, yeah, okay. And then we have a 0, because negative 0 plus 0 is still 0. Then negative 3 plus 3 is 0. And then negative 3 plus 4 is 1. Okay. Wow, a lot of 1 currents, aren't we? Okay. Negative 3 plus 4. Got it. Okay. And what do we want to happen next? That 2 becomes a 0. How do we make that happen? Negative 2 row 3 plus row 2 becomes the new row 2. All right, first entry, 0. Second entry, 1. Third entry, 0. Now the fourth, the one of interest here is, yeah, minus 2 plus 4 is 2. All right, and that just gave us I1 is equal to 1 amp, I2 is equal to 2 amps, and I3 is equal to 1 amp. And sure enough, that looks like it makes sense here, because coming in, you have 1 amp coming in, 1 amp coming in, 2 amps going out. That works. Now, of course, same thing here, 2 amps coming in, 1 amp coming out, 1 amp coming out. That is a net 0 there, too. And your loop around here is 1 times 3 is 3. 2 times 2 is 4. 3 plus 4 is 7. That's your loop there. And coming this way, 4 times 1 is 4. Plus 4 is 8 this way. Yep. Everything seems to balance. And we seem to have found our currents. Okay. I1 1 amp, I2 2 amps, and I3 1 amp. All right. That was a relatively simple circuit, though it had its moments. The next one's going to be a little more involved. Okay? So let's hit that. Example 7. This has 6 currents in it. Yo, everything got a lot more complicated, didn't it? So let's start off drawing the thing. It doesn't look that more complicated, but it is. Okay, we'll come down here, and we hit a battery going in that direction. And this is a 10-volt battery. Okay. Then we no sooner leave it than we run into a resistance. And that's 2 ohm. It's hard to read. Or the more I mess with it, the worse it gets, it seems like. Okay? That's your R1 of 2 ohms. Okay? And they label this as I1 going through it. And since the battery, the plus side is this way, that looks to be the right direction for I1 to be going. And R1 is 2 amps. Okay? Come down here. Hang a left. Not really. You don't have to have anything. Somewhere over here you hit node 1. So I1 is coming into node 1. leaving node 1 is I2. And it hits a resistor down here. And that resistor is 4 ohms. It's R2, yeah. R2 is equal to 4 ohms resistance. Goodness gracious. This happened yesterday too, about this point in my differential equations class. My head just started clogging up. I don't know what's going on. I don't know if it's something in the room or what, but anyway. So there's R2 being a 4 ohm resistor. And this heads north until it hits node 2. And that comes into node 2. You remember, well, actually comes out of node 2. Okay. Now, leaving node 2, you hit another battery, but this one's going in that direction, and this is a 17-volt battery heading to the right, and it runs into a resistor pretty soon, and that is resistor R4 is equal to 2 ohms. Okay. Goodness, my writing is terrible. Let me try it one more time. There, that's better. R4 is a 2 ohm resistor. Okay. Next thing you hit is node 3. Junction. No, they called it 4. I'm not sure I understand why they're numbering things the way they are, but it's fine with me if it's okay with them. That's 4. Okay. The current through R4 is I4. Okay. And we think it's going in that direction because the big side of the battery is this way, so that makes sense. That goes into node 4. Coming out of node 4, now this is the part that is not real clear whether they get it right or not. That's I5, and I was just trying to see here. They show that going south here. They show and that so far it looks like it's making sense. Okay. Then they get node or junction 3. Why they numbered them that way, I'm not sure. And then it leaves here, we think going in that direction, till it hits another resistor here, and this is R3. That's a 1 ohm resistor. Okay. And they call this current I3. Okay, and we think it's going in that direction. Okay. Last little leg over here, leaving junction 4, coming down and hitting a battery. This battery, the plus side's up, so this would indicate, if anything, this current should be flowing toward 4. Now they don't put an arrow there, which I find interesting. They do beneath it when they've got their resistor in here. And this is R6 is equal to 4 ohms, and I6 is, whoa, All right. Did something come over this way? Oh, there. I heard it click somewhere over there. I said, that really moved, didn't it? Okay. I didn't label this one. This is 14-volt battery here. Okay. R6 was 4 ohms, and this just comes into 3 here, or actually leaves 3, it appears. Don't do a real good job of, they have one little error over here on this, what they call path 3. Now that's what they're calling them. They're calling them, I call them loops, they were calling them closed paths, and so now they're calling them closed paths here too. And they, based on their battery configuration, say they think it's flowing like this in path 1, closed loop 1. They think it's going this way in loop 2, they call it path 2, and they think it's going this way in in path 3. And that makes sense according to the batteries. Okay. Now, if you notice, they have 6 different currents listed here. It's a lot of currents. So let's take the first node here, the first junction here, and we have coming into that is I1, so we'll put a positive I1, and I think I left off I2 here. I didn't write that in. See if I got all my other currents in. I think I do. Okay. Okay. And then we have coming into I1 is, into junction 1 or node 1 is current I1, leaving it, so we'll do a minus I2 and plus I3. Those are the 3 that are dealing with node 1. I1 coming in, so that's positive. I2 leaving, so that's negative. I3 coming in, so that's positive. That's it. So that's equal to 0. Long way over there. Okay. Now let's do node 2, or junction 2. Junction 2 has I1 leaving it, I2 coming into it, and I4 leaving it. Okay? So that looks like the second junction. Okay? The third junction down here has I3 leaving it, so minus I3. It has I5 coming into it, and I6 leaving it. So that's equal to 0. Junction 4, or node 4, whatever you want to call it, has I4 coming in, I5 leaving, and I6 coming in. So that adds up to 0. So those are our 4 junction equations. I can almost guarantee you they're not linearly independent. It's going to be some dependency on somewhere else. Because we've got 3 loops, that would give us 7 equations with 6 variables. So you know at least one of them's irrelevant. Now I didn't leave enough room to do, so I'm going to have to do my next one. So let's use their paths. We don't have to use theirs. We could have used other loops as well. These are reasonable loops, but we could have done this as a loop. We could have done this as a loop. We could have done that as a loop. You know, we could have done any loop we wanted to. These 3 make sense because they're lined up according to our batteries. They look like they make sense. Now, because I'm trying this have the variables be the currents, which is what I want, and the voltages are all constant. I'm going to do them again the way I did before, but you could do plus and minuses and set it equal to 0. Just seems to make sense. They're doing this as 1, 2, and 3. Okay, so loop 1. And I like to start just south of the battery, just below where the battery is. So here's a voltage drop of 2I1, and then you have a voltage drop of 4I2, and then that's equal to, where it's 10 volts. Okay, there's the first loop, or closed pathway, they call it, path. Okay, starting here, and I'm going to start just beyond the 17 volt, that's the 7, yeah. And this is going to be 2I4 plus, I didn't label R5, did I? R5 was 2, R5 is 2 ohms. Sorry. I thought something was missing there. I was thinking it was my current. So this is 2 plus 2I5. Yeah. Okay, continue on around. And plus I3. That's going to equal 17. Okay. That's, oops, no it isn't. I left off this one. Plus 4I2. Okay. So you have 4 voltage drops there, going the way we think it's going. 2I4 plus 2I5 plus I3 plus 4I2. Yeah. All right. Big one there. All right, let's start just north of that voltage. And the first drop you have is 2I5. And the only other one you have is plus 4I6 is equal to 14. So there's your 3 loops. We could write other loops, but those are going to be sufficient. We already got more equations than we have unknowns anyway. So what I'm going to do is set up a matrix. And this is going to be hard because I've been too generous with my writing here. All right. So the first one we have you tell me, using this as our first equation. One. Second. Minus 1. Yeah. I'm using these 4 equations here and those 3 here. I'm going to set up my matrix up there. So the first equation is, or line of the row of the matrix is 1, 1, and then 3 zeros, right? 4, 5, 6, and there's a 0. Okay. So there's actually 4 zeros there. Next one will be a minus 1, 0, minus 1, 0, 0, 0. Okay? Next, 2 zeros, a minus 1, another 0, a 1, minus 1, and a 0, right? Are we out of time? How are we doing on time? I think we're almost out. 2 minutes? Don't think we're going to finish this one, do you? Okay. The last equation will be, or row, will be 0I1, 0I2, 0I3, 1, minus 1, 1, and 0. Okay, let's just set up the next three quickly. And rather than write 2, 4, and 10, let's make that 1, 2, and 5. Is that okay? So that will be a 1 here, a 2 there, a 0, 0, 0, 0, and a 5. You okay with that? All right. The next one, can't do much with it, so it's going to be a 0, 4, 1, 2, 2, 0, 17. What a fun one. And the last one is going to be a 0, 0, 0, 0, and let's divide that by 2, 2, 1, 2, 7. All right. Obviously my, oh, it didn't take. Let me get this out of the way. Okay, and expand my brackets a little bit. There's our matrix. All right. Looks like a fun matrix to do, doesn't it? Okay. Actually, it's pretty easy because there's mostly ones. There's a few twos and sevens and other things like this, but in the main part, it's mostly ones, twos, there's a 4. So, you got a 1 here, easy to get that to be a 0. Easy to get that to be a 0, you have that one done. Now, I can't square, in fact, I should square, but when this becomes a 0, that becomes a 0 too, so you're going to lose that leading 1 there, but 1 will pop up somewhere else. If not, you can make 1. But that's the matrix we're going to do. Now, do you want to pick up and do that one next time, or do you want to do that at home and just pick up and go from there next time? Think you can do that? Okay, why don't you do that one? Let's just make sure we got it right according to the book. 1 minus 1, 1 and 4 zeros minus, oh, they didn't do the same way we did. They did a 1 minus 1, 0, 1. So, but mine's the same. It's just off by minus 1. I like mine better. Okay, and then they have the next one negated 2. They have a 1, 0, minus 1, 1, 0, same thing. And then 3 zeros, a 1, minus 1, 1, 0, same thing. Now, they didn't divide by 2, we did. 2, 4, 4 zeros, and a 10, that's the same. And then the next one is exactly the same, 0, 4, 1, 2, 2, 0, 17. And then the last one they didn't divide by 2, 0, 0, 0, 0. 2, 4, 14, yeah. That is the right matrix. You're going to work on that? So, well, we may, it's sort of a fun matrix to do, so we may do that. Now, do it yourself, but especially if someone else is here, we will start with that augmented matrix next time. Okay. And it won't take us too long to do that. Goodness, things are flying. Okay. You don't happen to have the book, do you? All right. Oh, do you have it with you? Okay. That is the last example of the section. So homework exercises, you do any of the odds 1 through 11. They're all at Calc Chat. Any of the odds 13 through, goodness gracious, well, 13 or 15, they're both at Calc Chat. Then you can do 17 if you'd like, it's at Calc Chat. Net profit if you want to, that's at Calc Chat. There's a guided proof, that's up to you whether you do that. That should be at Calc Chat. 23 is a calculus problem. If you want to look at that, you can. It should be at Calc Chat. 25 doesn't say much about it. You can do that if you want to. Then 27 and 29 are both network analysis. You can do either one of those if you'd like. Actually, 31 as well and 33. So any one of those, 27 through 33. And then temperature, we got a 35. It should be at Calc Chat. We didn't do partial fraction decomposition. You may have done that before in calculus, but you can try that 37 if you'd like, 39 if you'd like. Now that one has a Lagrange multiplier in it. That's the lambda. You can play with that if you'd like. But you know, they didn't do one of these like we're working on, did they? Huh, they did the other networks, but not well, I see. I'm sorry. 27, 29 are the other networks. 31 and 33 are your Kirchhoff law. Okay. Both of them look pretty simple, so you can do those. And then if you want to, you can look at temperature and partial fraction and calculus. We didn't do examples like that. But you can go from there. And I gave you your test last time? Okay, good deal. So actually it won't be due until a week from Thursday, because we'll finish this on Thursday, and then that's when your clock starts there. But you can take longer if you need to. And then we'll get going in Chapter 2. All right. That was a bit long today.